yesterday when we did that. So we can roll through that one real quick again. 1e negative 31 divided by 108. So s to the 5th equals 9.26 times 10 to the negative 34th. S, or solubility, is going to be 5 in math. Go down to 5. And then I would go with my answer. And I get 3 or 2. I want to say 2.5 times 10 to the negative 7th. Is that right or not?
Yep.
What's that? 1 sig fig officially. So it'd be 2. And that'd be moles per liter or molarity. Either thing. Same thing. Is anyone not getting that cubed root? Really yummy. Or not the cubed, but the 5th root. So that gets a little crazy. But in your calculator, which you all reminded me of it yesterday, once you have that answer that you're trying to do the 5th root of, press 5 for the 5th root, and then math, and then go down to the 5, and then second function answer, or just type in the answer that 9.26 times 10 to the negative 34 number. Courtney Bewley.
So on 25, they're solving for KSP, but does KSP have like a label on it?
Nope.
Okay.
Nope. KSP, just like other K values, has no label. It's just a number. Now, as far as comparing KSPs, again, notice how this KSP is really, really weeny. I mean, that's really small, but it's also split apart into 5 ions, not just 2 or 3. So you could not compare, again, like we talked about yesterday, couldn't say which one of these 2 dissolves more and just compare this to, say, AgCl, something where it's only 2 ions. Or which one, just looking at the KSPs. You'd have to actually solve for the solubility to figure that out. Or which one has the higher solubility or something like that. KSP, you can only compare when they break into the same amount of ions. So if we have something else that breaks into 5 ions, sure. Which there's plenty of those on page 746. Maybe not plenty. Maybe none. Oh yeah, there's a bunch. So there's others that have 5 ions for phosphates, calcium phosphate, barium phosphate, lead phosphates. Lead phosphate has a KSP of 1 times 10 to the negative 54. It's not much. Other problems from last night. So this was 20. Did I do 28? No, we were doing 28? Or what were we doing 28? Am I in the wrong number?
28C.
28C. I'm forgetting which ones I gave. Oh, I gave them even knowing. That's fun. 28C. Now, FYI, for your other knowledge, you can try the other ones. Let me give you the answers. Because they're not in the back of your book.
Which one is
28A is 1.5 times 10 to the negative 3rd molar. 28B is 2.3 times 10 to the negative 6th.
What was 28? What was A again?
28A, 1.5 times 10 to the negative 3. 28B, 2.3 times 10 to the negative 6. Other questions on last night's problems? So again, 19, 23, or 25? 19, 23, or 25?
Grams to moles. And then those moles, it's over 1 liter, so it's just, it ends up being 0.00151 for the NiOH3. And then after that, you basically just do it right like how you would.
All right. May or may not surprise me, but
So
we'll
it's
move on.
0.14 grams of NaOH, and you put it times 1 mole over 92.71 grams.
Yeah.
Oh, you got 0.00151 moles. Over 1 liter is just that's the molar. And then when you and then it ends up being square too. So it basically KSP equals 0.001 times 0.0032 squared.
I just want to talk in grams.
Oh yeah.
So now we're going to look at them a little bit differently, or we're going to look at different types and where an acid or base can make a difference, or another common ion can make a difference, or if something will make a precipitate or not based on what's in it. So we're going to come back to Q here in a bit. If you forgot about Q, we'll remind you about Q. And then talk complex ions for a real tiny bit, and then we'll be done. You should have some time to work on your problems for tonight. Well, hopefully. I just have to not talk so much, right? So, we have number 36, COOH2. And solubility constant, so we have CO2 plus 2 OH minuses. And we are looking for what's its solubility when it has in a solution with a pH of 11. So what's that changing, folks? What do you think? pH is 11. What's that going to change? Yeah, we're going to have some OH present originally. So, I don't know if you remember from other common ion things, but if there's already some OH minus in the solution, that means that's not going to dissolve as well as it would have in plain water, because there's already there's already some of those ions there. It's not going to dissolve as well. This would still be 0. This would still be S. This would still be 2S. We're using S for solubility just because that equals how much it dissolves over here. But the pH equals 11. That means POH equals 3. It's a whole number. So that means OH minus, we can do the math, but second log of -3 is 1 times 10 to the -3. So this is 1 times 10 to the -3. So this is 1 times 10 to the -3 plus 2S. We are given a KSP of 2.5 times 10 to the -16. So I'll just write it all out. KSP equals CO times OH minus squared. And of course, I'm out of my head. 2.5 times 10 to the -16. Now we're just start plugging things in. This is S. That is 1 times 10 to the -13 plus 2x, 2s. Just like all of our other problems in the past, we're going to assume that's negligible. That 2 times that number is too small. So this is really going to be times 1 times 10 to the -3 only squared. And I'll solve for S. Tell the people at your table if you think you're right. If you don't think you're right, just compare. Chase, did you get an answer?
Not yet.
Not yet. Reagan? 2.5 times 10 to the -10. Sounds good. And again, since it's solubility, it's moles per liter or molar.
I didn't go with that.
I got 2.5.
Yeah, I
me
got that
too.
too.
Yeah, I got 2.5.
Oh, I did something wrong. Is it? This is a 16, isn't it? Is this a 16?
Yeah.
My bad.
Okay.
Sorry about that. I wrote the KSP wrong. So it would come up be -10 with that 16 in there. So we could figure out what it would have been without the OH minus, but it would be a higher number without that OH minus. So less of it would dissolve with the OH minus in there already when it's in a base. So if there's that is like a regular common ion, but in this case it's an acid or a base, and the OH minus or the H plus would affect it if there's extra of that there. So it's very similar to other common ion stuff we've done in the past. It's just ions that are already there, and it's going to affect how things dissolve. Let's look at 44 real quick. 44. What do you think? First group, and any reasons why. One of those would be affected by pH. One of those, or the other two would not. It would depend on pH. Any ideas? Which one would be affected and why? Kayla, what do you think?
I'm guessing AGBR just because the other two would come from strong acids.
Well,
But I was just guessing.
the other one, you're right in your reasoning, just the wrong pick. Yeah,
BAG.
yeah, the AGF
Oh yeah, because that's the one that doesn't come from I
will
forgot.
come from a strong acid. So why does that matter? Well, if you have a acidic solution, well then some of the H plus is going to combine with the F minus and make HF. So it's going to be pulling some of that F minus, so it's going to cause the AGF to dissolve a little better because there's not any F minus in as not any, but there's less F minus in there as ions. So if you had an acidic solution with that, it would affect it. But we know that Cl minus and Br minus, since they come from strong acids, no desire to be with a hydrogen. So even if there were hydrogens present, it wouldn't affect it. It wouldn't have any effect on it whatsoever. So in that case, with these salts, we're just looking for the ones that would have an effect must have an anion that is coming from a weak acid. So look at the rest with your people real quick. Which ones of those do you think would have an effect? Or it could have another issue, but either coming from weak acid or we'll talk about B. Think about it with your people. Which ones do you think would have an effect?
Why are you doing C?
So B, C, and D, what do you think? How about letter B? Which one do you think would have an effect? Melissa? No. It would not depend on pH. The reason why B, and I was just talking about the weak acid part, but letter B would have an effect just for the same reason we just did number 36. You've got some OH minus present if it's a base, if it's a pH is high, or even if it's an acid. So it would depend either way. If it's an acid, there's extra H plus in there, and that would combine with the OH minus. If it's a base, there's extra OH minus already in there, and it's going to not dissolve as well. So either way, it would be affected. So the one with the OH minus or the PbOH2 would be affected. As far as C and D, it's just like A. You're looking for something that has conjugate base of weak acid. That means that it would be basic and it would join with hydrogens. So SrNO22 for letter C, NiCN2 for letter D. The reason why is because the nitrates coming from a strong acid in C and D, those nitrates would not join with hydrogens. They would not be affected. They have no desire to be with them. Not a strong enough attraction for any hydrogens.
How are we able to determine that?
Which ones?
Like C and D?
C and D. The nitrate ion is coming from a strong acid, nitric acid, and it would not. That means that hydrogens and the nitrates don't join together well at all. So even if there's a bunch of nitrates in the solution, or a bunch of hydrogen solution and nitrate would not join with them at all, react with them at all. But if you had a weak base there, it'd go find some hydrogens. And that would affect, if those guys joined up, it would affect how much of the other stuff dissolved. Alright, a couple other thoughts here, or concepts. Let's do number 38. I'll do A, you guys will do B. 38. 38A. So pretty much the same type of idea, it's just not an acid or base, it's a common ion. So we have PbI2, it's going to write the same way with the ice stuff. It's going to make Pb plus 2 I's. Calculate solubility in each of the following. Well, I'm not going to do water. We've done that before. Well, we could. We could do that just plain Jane, just as a quick review, and then calculate it with 0.1 molar lead nitrate, and then have you guys do letter C. So, 1.4 times 10 to the negative 8 for KSP. So, normal solubility, or S, is going to be broken apart, and it's going to make S, it's going to make 2S, we have S, we have 2S, KSP equals PB times I, but that's the second power. Now I plug everything in, 1.4 times 10 to the negative 8 equals S times 2S to the second power. So all this is going to equal 4S cubed. And then S equals something. .4 e negative 8 divided by 4. Third root. I get 1.5 times 10 to the negative 3.
Yep.
I like that. So now, well, I'll be lazy. Or I won't be lazy. I'll write it all out real quick. PbI2, Pb plus 2 I's. Now, how does that change for letter B? What's changing now?
Adding lead in the initial solution.
There's lead ions now? Okay. So since we have 0.1 molar lead nitrate, that means that the lead would be just 0.1. So this would be 0.1, 0, S, 2S, 0.1 plus S, 2S, and pretty much the same problem. We'll keep out the other part. And this equals 0.1. I'm going to assume the S is negligible, times 2S cubed. And let's see what S is now. 1.4, negative 8. Help me out, make sure I'm doing my math right. I get 1.9 times 10 to the negative 4. You guys getting the same thing? Nope. So, tell your people real quick at your table why these numbers are different. Why one of them is larger than the other or smaller than the other. Looks like letter B, the number is smaller. Why is that? Just real quick. Tell each other why that number is smaller. Take conceptually. Why is that smaller? Why is that number smaller? Which part, Kayla?
My calculator is just not working out. Wait, does that say
1.4 times 10 negative 8.
2s?
2s cubed. So when I did it, I go 1.4 times 10 negative 8 divided by 0.1. Then I said divided by 4. Since 2 squared is 4. And then I took the square root of that. Gabby, what do you think? Why is one number smaller or bigger than the other?
Because we added lead, so it's less valuable.
Yeah, essentially, there's already lead ions there. So it's not going to break apart as much. The original lead iodide is going to break apart as much because there's already some lead iodide there, or lead ions there. Same thing happened when we talked about weak acids, weak bases. We talked about common ions before. When there's already some other of the ions there, this doesn't break apart as much because there can only be, because the KSP equals a certain number, there can only be a certain amount of those ions in solution. If there's already some there, not many more can go there. So that's why the solubility in the second part is going to be smaller. Try letter C. Try letter C. Some of you may have already done that, but give it a try real quick.
I don't know if you could figure it out. It says 1.4 negative 8 plus 0.1 times 2 is 2. So I divide by 0.1 and then I divide by 2.
Oh, I would probably do the 0.1.
For letter C.
Oh, 0.2 squared. What is it?
Hold on, I didn't do that out, but I think you have to factor that out. I would factor it out. 4s squared, that's 4 squared, and then 0.1 times 4.
I don't know what we did there.
That would be 0.4 s squared now. And then 1.4.
Oh, I was, okay. I got it. No, oh yeah, I got it.
Or
I didn't do the
Yeah, that's what.
it was just 0.01 squared.
Can we assume any of these are numbers?
Anything you can add to the rest.
Do we have to
Some sort of S.
original too? Original with calculator?
Say that again.
Do we have to do the original with calculator? Because in a room it just says calculate with 0.1. Or sorry, calculate it with 0.01 molar. Couldn't you just
Yep, you put it in the same, and you put in 0.01.
Oh, it's just the iodine that we care about as far as our equilibrium of solubility. So if you rewrite that equilibrium of solubility, I just made the changes up here.
Which one can I try?
how'd you know in the first one on the right, it was the lead, and then now it's the iodide for the NaI?
Because out of the lead iodide, the the only ions that matter, that would affect its solubility, would have to be the lead or the iron. So in letter B, when it was lead nitrate, the nitrate ions aren't going to affect it. It's just going to be the lead.
Oh, okay, that makes sense.
And now for letter C, it's sodium iodide. The sodium's not going to affect it, just the amount of iodide there.
Oh, I thought it was iodide, it's nitrate.
So which part are we assuming negligible?
Okay, we're going to go through now. All right, folks. Shh. I made changes for letter C up here. So instead of writing it all, rewriting it out, I just made changes in this beautiful lavenderish color. So now the iodine, since it's 0.01 molar sodium iodide, the sodium ions would not affect the solubility, but the iodide would. The fact that there's iodide ions there, there's 0.01 there. And we're going to add that to 2s still, like we did before. And now we have 2s, or 0.012 plus 2s. I just switched it around compared to what I normally do. But again, like many of the problems and any problem that you're going to see on the AP test, you can assume when you're adding an x or you're adding an s or a 2s or a 3x or those things, you can assume that they're negligible, that number is negligible. So this 2s number I took out. So now I have KSP equals S, which is my PB2 plus, times 0.01 squared, because the 2s is, we're assuming, is negligible. And when I do the math later, it does work out that it is negligible, because what I have to do is look at my S that I got and divide it by what that 0.01, it's less than 5%. So if I have S times 0.01 squared, solve for S, I should get 1.4 times 10 to the negative 4. Again, the molarity goes down, and it should, just because there's already some ions in there. The equilibrium constant is not going to change. So if you already have stuff dissolved, less of it's going to break apart. There's already some of that ion in it. Other questions on this idea? Common ion. Essentially, the acid and base was pretty much a common ion thing too. It's just hydroxide or hydronium have an effect. Sometimes an indirect common ion too, but very similar idea. All right, we're almost there. We're almost out of equilibrium, believe it or not. Which other one I want to do? 50. I'd like to do 50. I want you to read 50 real quick and see if anyone would have an idea of how we could determine that. We erase all this, just look at 50. Looking at 50. Looking at 50. Any ideas? How would we determine if a precipitate would, or if something would precipitate, if it make a solid or not? Go ahead.
You set it up to Q or whatever that, and basically solve it with the initial amounts. And
Okay.
if it's higher than the KSP value they give you, then they will do a precipitate, and if it's lower, it won't.
Perfect. So let's do it real quick. Let's look at that. Number 50, we have cerium iodate. Very common substance. Maybe somewhere, I guess. But it's going to break into cerium 3 plus 3 iodates with a minus charge. But they give us the amounts. We know the amounts given at this point. Q, from your past, Q is just a certain position. Doesn't mean it's at equilibrium. Could be shifted left or shifted right of equilibrium at this point. We want to see what Q is. Q is going to be solved just like K, KSP, but you have these conditions given, and then from that, we analyze what's happening. So Q, just like KSP, would equal those ions, and then the iodates to the third power. But they give us these things. They give us the cerium and they give us the iodate. So then it's just a matter of making a decision if we think it would make it precipitate or not. Ce is 2.0 times 10 to the negative third. And the iodate is, where am I? 1.0 times 10 to the negative 2. isn't as crazy as it looks. This is 1 times 0 times 10, or 1.0 times 10 to the negative 6. Multiplying that by 2 times 10 to the negative third, I should be getting 2 times 10 to the negative 9. So Q equals 2 times 10 to the negative 9. KSP, which gives us the balance of the maximum amount of ions that could dissolve before we have a solid, is
Wouldn't we have to
3.2 to the negative 10.
3.2 negative 10. Go ahead.
Wouldn't you have to multiply the 3.0 times 10 to the negative 2 times 3? Because we have 3 of them up in the balance.
No, but that is a great question. So let's talk about that here in a bit. 3.2 times 10 to the negative 10?
Yep.
Okay. So this represents, this KSP represents the balance of those cerium and iodate ions when you multiply them together, the maximum possible that could dissolve. Since our Q is larger than that, and it's 2 times 10 to the negative 9th, some of that would precipitate and make a solid, so that the number of ions would be equal to this KSP. So there'd still be some ions in the solution, but some of it would precipitate until it came back down to that equilibrium that's expected, which is 3.2 times 10 to the negative 10. But we would get a precipitate, because this just indicates there's too many ions. When the Q is higher than KSP, there's too many in solution, and that amount can't dissolve. Your screensaver, I don't know if I'm supposed to touch it around, but anyway. So now, Jess's question. They gave us the actual iodate amount. The reason why in the past we said this is 0, this is 0, this is 3S, this is S, 3S with problems in the past is because they would tell us what the solubility is, or they tell us the KSP or something, and we'd have to take into account that there's 3 iodates for every 1 cerium. And we'd have to use that and multiply it by 3 to be able to figure that out. In this case, they've already given us the iodate. There's no need to multiply by 3 or anything because they've given it to you. But it is a weird, I understand it's like, how do we know when to do that, when not to do that? But when they straight up give it to you, you can just plug it into Q or the KSP equation. If they're going to give you the amount. I'll get that. Drum Notch. Someone's messing with me. So one of your problems you're going to do for tonight is similar to that, number 49. Very, very similar thing. Number 49. Okay? So you're going to be able to give lots of things a try here. I want to talk about one last thing before lunch. And then after lunch, you'll have some time to work. But if you don't want to use it, I'll have you do I'll do some AP things with you instead, practice. But I'd like you to take the time, ask questions, and try them yourself or try them with people around, rather than trying them tonight and it's like, you get frustration. All right, last thing in chapter 16, last concept in equilibrium. Last thing, do some sort of equilibrium, end of equilibrium party here. So after lunch today, you'll have some time to work on problems. Tomorrow, KSP lab, but then I will for homework and in class, so we'll see about class, but for homework you will have some AP practice. And from kind of all of equilibrium, like it or not, but definitely include some KSP problems from the past, from practice AP. And on Monday, we'll get into chapter 17, which is totally different. We've been stuck on equilibrium type of things for so long.
When's the quiz?
Tuesday.
Thank you for not making me the Monday quiz.
Well, you just get a little bit of 17 sprinkled in, but it's not much. All right. So, Complex ions. We brought up complex ions way back when we talked about Le Chatelier's principle. I remember these guys had the lab that they did, and they made a complex ion when they did the Le Chatelier's part. But we're just going to talk real quickly about how it can affect solubility a little bit. So a complex ion again, a metal ion, which is acting as a Lewis acid, because metal ions like iron and aluminum, they don't have any electron pairs to donate, so they could accept them. So a metal ion bonds with ligands. And those ligands are Lewis bases with electron pairs to donate. Examples, I'll just put down here. Chlorine's a common example. Ammonia is a common example. Remember, chlorine's got 4 lone pairs. Ammonia's got 1. Water's got 2. So those act as good Lewis bases that combine with those metal ions. So let's talk about an example of how that could affect a situation. Silver chloride. It's one of those that we've used throughout the semester. We know that it is insoluble in water. And that's what we're talking about when we're talking about KSP. We're using things that are pretty insoluble, but there's some degree of ions that could be in the solution, but not much. So this is our normal KSP for silver chloride. But what if those silver ions made a ligand or made a complex ion with something? So this is in water. In water. But what if we put it in ammonia? We had some ammonia ions. In that case, some of the Ag plus would join up with ammonia. And I'm taking this straight out of your book, and some of you may have already seen this, but it's going to join up with ammonia and Ag and H3. So we have plus. Now this has a K value of 2.1 times 10 to the negative, or times 10 to the third, or 2100. What does that mean to have a high K value? What's that mean is happening?
Coming together?
Coming together, yeah. These two things come together pretty darn well to make this ion. Alright? And remember from back when we talked about it with hydrolysis and Lewis acids and how it works, typically they'll bond to twice as many of their charge. So now let's take it one more step and show this AgNH3 plus joining to one more ammonia. That's typically what it would do. Twice as charge. It's not a definite always, but you could, if you assume it, you'll be okay. And the K value for that is 8.2 times 10 to the third. So that becomes even higher. So even more ammonia, but then if there's more, if you think about Le Chatelier's, if this is joining with more ammonia, that means that there's more silver ions being removed. How is that going to affect the solubility of silver chloride if I dissolve it in water versus dissolving in ammonia? Yeah, it's going to go up big time. Because while it's not helping the chloride ion option, in this case, because chloride's not acting as a ligand in this case, but in this case, the ammonia is acting as a ligand with the silver to make this complex ion, and different things can make different complex ions, and don't try to memorize them or anything like that. Know that it's about twice as much as far as the charge. So when we did Lewis acids like aluminum, which is in your antiperspirant, Aluminum's a 3+, so it had 6 waters that surrounded it. Typically, it's twice the charge as far as how many ligands will surround it. In this case, there's a 1+, so twice as many as the most stable complex ion. But when you're pulling out those extra silvers, that's just going to allow this solid silver chloride to dissolve more.
Wouldn't that be a 2+ charge? You already had a 1+ charge on the left side.
I know, but those ammonias are neutral, so it's not going to affect it at all, the charges. So while the chloride isn't being helped here in any way, as far as taking it out of solution, as these silver ions are taken out of solution, and then these complex ions are soluble. And so that's taking these silver ions out, so it causes more and more of this silver chloride to dissolve. So the formation of complex ions can also affect solubility. So you have a normal solubility, that's regular KSP. How much something would dissolve in water? Well, if there is a hydroxide in that substance, well then it could be affected if it's an acid or a base. If it has a base in that salt, well then it could be affected if it's dissolved in an acid or base. If there's already other ions present, like we talked about with the lead and iodide ions, well that'll affect. It's not going to break apart as much as it normally would in water. And now another effect on solubility is if it has the possibility of making a complex ion which is soluble, it could cause things to break apart more. A lot of hooey. Kind of crazy talk. So you'll be able to see tomorrow not only how we figure out KSP, but then some kind of AP type of questions that KSP could be involved in. They're typically not too crazy, but they throw in complex ion stuff here and there. But just having the basics behind it, you should be just fine. Questions on that? So it depends on the metal ion, what type of ligands. So when we talked about hydrolysis, we had copper, iron, aluminum, something else from that lab, that all joined up with water, had water as a ligand, and then with that ended up becoming an acid because of that. Here we have silver ions, which aren't acidic typically, or neutral, but now they have ammonia that gets surround. So it depends on the metal ion what they will attach with and what the effect is. All right. So problems from last night, problems for tonight. I'll probably go grab copies so you can look at the lab for tonight if you desire. But problems for tonight and things to look at: 16.3. Notes, and 33 through 39, odd, and number 49. So I'd like you to take your time, or take some time after lunch and practice, and have each other, and try to, and have me around to try to do problems on your own. See how it goes. You want to stop that, Jess? I can do it.